All right, section 4.3 has us looking at the first derivative test. And if you really think of the derivative as like slope, it's really instantaneous slope. If you think of it as slope, when the first derivative is positive or when the slope is positive, then your graph is going up. Or we would say that the function is increasing, so the y values are getting bigger. If the slope is negative, or if the first derivative is negative, then the graph is going down, which means it is decreasing. Y values are getting smaller. And when the first derivative is 0, that would mean that the function is horizontal during that time. When the slope of the tangent line is 0, that's when we have a horizontal tangent line. Okay, so keeping these things in mind, we're going to continue on with our work with critical numbers. And critical numbers don't just occur when the first derivative equals 0, but also when the first derivative is undefined. This one is sometimes forgotten. And how we're going to use critical numbers with the first derivative test is that the extrema, the max and mins, often, but not guaranteed, occur at critical numbers. So for example, if I wanted to find the critical numbers of y equals x cubed, I would find the first derivative, and then I would think about where the first derivative is undefined, and that doesn't happen, and I would think about where the first derivative is 0. So that would be when x is 0. Okay, so that is a critical number. But I'm picking a very simple graph here, y equals x cubed, which looks like this. And so we can visually see that just because this was a critical number didn't actually mean that it was a relative max or a relative min. This couldn't be a max because the point after it is bigger, and it couldn't be a min because the point before it is less than. So critical numbers are usually relative maxes and relative mins, but not always. So we have to have a way to test, because most functions are not as basic as y equals x cubed, where we can just graph them really quickly. Okay, so suppose c is a critical point and f is a continuous function. That's important so that we know it's not jumping around in ways that is unpredictable for us. And we're going to do this to find the local maxes and the local mins, or the relative max, relative min. Relative and local are interchangeable. All right, so if the derivative changes from positive to negative at c, then f has a local max. So think about that. If the first derivative is positive, the graph is increasing. If the first derivative is negative, the graph is decreasing. So if the graph was going up, but now it's going down, and that happens at c, then that's a max. It was going up, now it's going down. Okay, so let's look at this example. If we found its critical numbers by finding where the first derivative is 0 and undefined, looks like the first derivative equals 0 at 0. So 0 is likely to be a max or a min. But the way that we're going to test, since, well, we kind of know what this graph looks like too, but when it's too complex to test, we're going to take a point to the right of each critical number. Doesn't matter, just pick something easy. And to the left of each critical number. Again, just pick something easy. Don't pick negative 3/8. Don't pick negative 100. Just pick something easy. Well, we're going to throw these numbers into the first derivative so we can see what's going on with the graph. So if I plugged 1 into the first derivative, I get negative 2. Now, I don't care so much that it's negative 2, but more so that it's just negative. If it's negative, the graph is decreasing. And then I will plug in negative 1 into the first derivative, and that would give me positive 2. Again, I don't care so much about the 2, but I do care that it's positive, which means it's increasing. So if the graph was increasing until I hit 0, and then it started decreasing, then this critical number, x equals 0, is a local max. So I may not know what the rest of the graph looks like, but from the first derivative test, I can tell you that that is a relative max or a local max, whichever you want to call it. Okay, so let's switch it up. Let's say the first derivative is negative. That means the graph is decreasing. And then it switches to positive at C, so then the graph is increasing. Well, if the graph was going down and then it starts going up, we would say that that is a relative minimum. So let's see how this would work out. So critical number is going to be something you hear a lot from me the rest of the semester. So when the first derivative is 0 or undefined, so we've got to be able to take a derivative. We've got to be able to set this equal to 0, and it looks like when x is 0, the first derivative is 0. So if 0 is a critical number, it's likely to be a max or min, but to be sure, we need to test a point to the left and a point to the right of each critical number. Sometimes you have more than one critical number. So now if you plugged 1 into the function, you get 1/6. That's a point, but that point doesn't tell me if the graph's going up or down. I want to plug 1 into the first derivative, see that the first derivative is positive, and if the first derivative is positive, I know the graph is increasing. Then on the other side of the critical number, I want to plug -1 into the derivative, see that the derivative is negative, and when the derivative is negative, it's decreasing. And now I have a visual. It's going down till it gets to 0, and then it's going up. So when x equals 0, I can see this is a relative min. All right, and it's possible that it doesn't change signs at all. We saw that with x cubed, but let's go ahead and actually work it out instead of just looking at the graph. But if it doesn't change signs, then it won't be a local min, nor will it be a local max. Okay, so for this one, it looks like it also has a critical number at 0, because that is where 0 is a critical number. That's what makes the first derivative 0 or undefined. I know undefined doesn't come up much, but you got to say that to yourself each time so you don't forget it. I could test a point to the right, like 1, and I'll throw it into the first derivative to see that it's positive and the graph's going up there. And I'll test a point to the left of the critical number, like -1, and I'll plug that into the first derivative, and it's also positive. So it's showing me that before 0 is going up, and then after 0 is going up. So that's not a relative min because it didn't max out. Up and up or down and down is not going to be a max or a min. So that's how that will look to play out for that. Now on the AP test, when you're talking about increasing or decreasing, you need to make sure that you just say exactly what you mean. Don't use the word it. Don't say it is increasing, it is positive, it is this, it is that. You need to say the first derivative is positive, the function is increasing, the function is decreasing, the first derivative is negative. You got to be very clear in your thoughts, because saying it, graders are not allowed to just assume that you're talking about the right thing. So I'll have to do the same thing for you guys on the test. Okay, so I'd like you to pause now and go ahead and find the critical numbers in number 4, and then test around each critical number to see if you can find the maxes and the mins, which would be all the local extreme points. All right, so to find critical numbers, that is when the first derivative is 0 or undefined. So you should have found the first derivative. You should see that this is never undefined, but it is 0 when x is plus or minus 2. Forget when you take the square root of both sides, you got to do plus or minus. So this one had 2 critical numbers, 2, -2. So 2 places that might be a max or might be a min. So you should have tested around this critical number, so it doesn't matter which number you pick, but I'm going to pick something easy. like 0 and 3, so I have something to test around it, and then you need to test around this one too, so maybe 0 and negative 3. Now be careful not to plug 0 into the function. That gives you a point, and while a function, or having a point isn't bad, it doesn't help me understand the behavior of this graph. It just gives me one tiny instant in this. But if I plug something into the first derivative and see that I get a negative value, well, when the derivative is negative, it is decreasing. Or plug in 3, when the derivative is, plug in this in, that would be positive, and when the derivative is positive, it's increasing. And plugging in negative 3 would also be positive. Again, I don't really care so much about the number, I just care if it's positive or negative. But if the first derivative is positive, the graph is increasing. And now I've got the shape of my graph. It was going up, then down, then down, then up. So it looks like negative 2 was a relative max, up and then down. And then positive 2 is a relative min, because it was going down and then up. Alright, so go ahead and pause and try to learn from your mistakes on number 4, and then give it one more go on question number 5. Alright, so extrema points can only occur at critical numbers. So we needed to first find critical numbers, which involves us taking derivatives, bring the power down, lower the power by 1. I'm going to go ahead and move this down. And chain rule here. So times 2x. So this would be 2 times 2x would be 4x. Alright, so got to be able to do derivative, power rule, and chain rule on there. Alright, so when this equals 0, or when this is undefined, is when we may have maxes or mins. Those are our critical points. Well, a fraction equals 0 when the numerator equals 0. So it looks like 0 is a critical number. 0 is a critical number because it makes the first derivative 0. But also, if I can make the denominator 0, that would make it undefined. So I also have to figure out where that happens. So I could multiply both sides by 3, or 1/3, divide both sides by 3. I could cube both sides, could add 9 to both sides, could take the square root of both sides, and it looks like 3 and negative 3 are also critical numbers. So remember, these are likely to be maxes and mins, but it's not a guarantee. So we have to test around these points. We got to test around 0, so I'm going to try like maybe 1 and negative 1. I got to test around 3, so I'll try maybe 1 and 4. And I got to test around negative 3, so maybe negative 1 and negative 4. Whatever values you think are going to be easy to do. But these values we're going to plug into the first derivative. Because if it's positive, it's going up there, and if it's negative, it's going down there. Okay, so if I plugged in a negative 4, my numerator would be negative, and looks like this would be squared, so this would be positive. 16 minus 9 is positive, the cube root of a positive is positive, times 3 is positive. So you end up with a negative over a positive, which is negative. Now again, you know, normally we care exactly what that number is, and I only care to do enough work to see that it's negative, because then that tells me the graph's going down there. If I tried negative 1, that would make the numerator negative, and you see this would be 1 minus 9 is negative, cube root of a negative is negative, so a negative over a negative is positive. So I can tell the graph starts going up at negative 3, and you shouldn't assume that it comes back down at 0. You need to actually test it. So plug in 1, that would make the numerator positive, and the denominator negative, so this is decreasing. And if I plugged in a 4, numerator would be negative, denominator would be positive, so that is positive and increasing. So negative first derivative means it's going down, positive first derivative means it's going up. And now I can see the shape of the graph. So not like how high it's going up, not the y values, I don't know any points, but I do know that it's bottoming out here at -3. So this is x equals -3, say relative min, tops out at 0. So x equals 0 is where there's a relative max. And then it bottoms out again at 3, so another relative or local min at x equals 3. Now if you wanted to know the actual max or the actual min, that would be the y value. But if you wanted to know the y value for those x values, you just plug those into the function instead. But this is when they occur, and that's the hardest part to find that. So that's the first derivative test. We've got this little way to show our work here. This is pretty standard practice to show your work this way. They do accept this on the AP test for showing work. So you just kind of got to get familiar with testing out critical numbers in that way, and back up to questions 1, 2, and 3. You got to have those things memorized, and then that should be about it.